Hi, it's Dr. Harris, and this is our first Math 111 video. You've seen, I think by now, some instructions through Canvas about how to do some setups and things, but I just wanted to go ahead and get us started logging into RStudio so we can look at our first slideshow and I can talk us through some of that. So just a reminder, you've seen these instructions already, but you want to use either Firefox or Chrome as your browser for this course. And we're going to go to rstudio.georgetowncollege.edu:8787. And that's where I am right now. If you type that into your web browser, again, Chrome or Firefox, you'll see this screen. You'll want to enter your Georgetown College username and your Georgetown College password. Click sign in, and you will soon be taken to a screen that looks something like this. And so just wanted to get us to the point where we can get to our slideshow and then talk through it. And so we see down in this lower right corner window with several tabs on it: files, plots, packages, etc. Before we get started, let's click on the Packages tab, and let's scroll down and check a couple of packages. So we're going to scroll down to the M's, and we're going to get to Mosaic. We're going to check this box next to Mosaic, and then we'll see some things going on in the console over on the left. It's loading some packages for us. And then we're going to scroll down into the T's, and we're going to go to Tiger Stats, check that box, and then we will check Tiger Data as well. So we want to make sure that we check Mosaic, Tiger Stats, and Tiger Data. This is something that we may want to wind up doing just about all the time. And then we're going to go to the Files tab, and we're going to get our slideshow and open it up. And so over here in the bar, the right end of the bar, you'll see a dot, dot, dot. If you hover over it, it'll say go to directory. We're going to click on those three dots. You're going to get used to this, I promise. And we get a go to folder box that pops up, and we're going to type in /cocom. The slash is the / that's right underneath the question mark on your keyboard. We're going to click OK. This is going to take us to the common folder. And one of the folders that we're going to be primarily interested in this course, is Dr. Harris stuff. And so we're going to click on that. And then we're going to see that there is a folder for Math 111. We're going to click on that. And we're going to see we got slideshows. So we will click on slideshows. And here's where the various slideshows that we're going to have over the course of our class are going to be residing. I've got 2 in there right now. And we're going to start with Open Intro 4, Intro Data 1. So this introduction to data is chapter 1 in the text. We're going to look at the first slideshow. I've already got this opened up here, but you'll just click on this and you'll choose View in Browser. And that will bring it up into your browser. I've already got it here. Introduction to Data, Part 1. And so I'm just going to talk us through the slideshow now, and we'll be interacting with RStudio some as well. So this is meant to be an introduction to the course as well as the beginning of chapter 1. So what are we going to be doing in this class? Well, we're going to be doing statistics, not surprisingly. And one definition of statistics, we're going to talk about a couple of definitions, but one definition of statistics is it's the science of data. And so we need to know what data is. And a good definition is that data is information collected about subjects that are under study that can be used to formulate conclusions about scientific questions. And then statistics, then we could say, is the science of data. We'll be doing various things with data in the course. So that's what we're going to be doing in this course. We're going to be learning how we can collect, analyze, and draw conclusions from data. And as I note here, we're going to occasionally be looking at a couple of variables at a time. A frequent question will be, is there some sort of relationship between a pair of variables? Another definition that you could use for statistics is that it's the science of uncertainty. And so we want to keep in mind as we go through the class that when we make statements, there's always a little bit of wiggle room, and we're not being completely definite in most of the statements that we're going to be making in this class. And so we want to realize that when we're drawing conclusions that are very likely to be true, but are not necessarily automatically true. So I want to start by looking at a couple of examples, example questions that we might encounter in this course. I'm hoping that we'll be actually working these problems by the time that we're done with the class. So you can read this description here. We've got a public parking garage that's been built in the hopes of revitalizing a downtown area, and the city is hoping to recover the cost of construction by charging people fees to park in the structure. And so a year later, after the structure is in place, they look at data from 60 weekdays that are chosen at random, and they look at the average amount of money that's been collected in parking fees on that day. And so for each of those 60 days, they recorded a value. The average value turns out to be $126 with a standard deviation of $20. Now, we may or may not know what a standard deviation is. We'll be coming to that in a chapter very soon. But here are a couple of questions that we might want to ask about this scenario. We don't necessarily expect that the overall average take is $126 per day, but we might want to know, well, what range, based on the data that we've collected, what would be a reasonable range of values that we think the true average might live in? So we think that, well, if the average isn't exactly 126, it's probably between this number and that number. And we want to try to learn how we can construct this number and that number in this class. How far away should $126 be from the actual overall mean income per day? Another scenario that we might investigate is that before the structure was built, a consultant was brought in, and they estimated that $130 would be the average income from the structure on a weekday. And so we want to know, is the $126 that we got, is that somehow a signal that the $130, not necessarily promise, but the $130 that was projected by the consultant, is that a reasonable figure or not? Could that $130 still be a reasonable figure based on the $126 that we got from the 60 weekdays? Or is it unreasonable to think that $130 is really what we could get out from these fees on average? So this is one type of scenario that we might be able to use statistical techniques that we're going to learn in this course to answer. Here's another example of something that we can use statistics for. This is in some ways a medical experiment. We've got 176 people, all suffering from carpal tunnel syndrome in their wrist. We're going to divide them into two groups, and we're going to apply two treatments, one treatment to each group. We're going to perform a surgery on people that land in the first group, and we're going to give a splint to the people in the second group. And we're going to come back a few months later and ask these people, have your symptoms improved? And so suppose that we collect some data from these people, and 80% of the surgery group reports improvement, while just 54% of the splint group does. And so a natural question to ask is this evidence, that surgery, people who undergo the surgery improve at a different rate from the ones who wear a splint? Certainly in the group that we have, there's a difference in the percentage that reports improvement, but is this a wide enough difference to believe that there really is something different about surgery from the splint? Again, we'll be looking at these sorts of questions like these. We'll be able to answer this question by the time we're done with this course. So a couple of important ideas that are implicit in the scenarios that we've just looked at, and those are of population and sample. A population, as you see here, is the entire set of individuals that are going to be under study in a research question. We're going to learn pretty quickly, though, that it's impractical to try to gather information from everybody in the population. And so what we content ourselves with is we collect information from a subset of the population, which we call a sample. And so we want to keep in mind through any scenario that we're looking at, what's the population under consideration? What's the sample that I've drawn? And I'm going to be asking you to consider these questions on the two scenarios that we just examined. In the parking garage example, what's the population and what's the sample? And then the same thing for the carpal tunnel example. What are the populations under study? How many are there? What are the populations? What are the samples that are involved? And so when we get together for our first class meeting, I'm going to be asking you to tell me what the answer to these questions are. So please think about this as you go through as you're going through preparation for class. Another important idea that's illustrated in these scenarios is the notion of variable. A variable is a value that we would collect from individuals in a study that could possibly vary from individual to individual. And there are going to be two primary types of variables that we're studying in this class. One's numerical. Makes sense that a numerical variable is one that takes on numerical values, whereas the other type of variable is categorical. And we're going to call the values that a categorical variable can take on levels. We'll often call them levels. And the levels are the categories into which individual observations may fall. And so I'm going to be asking you to think about these scenarios again. What were the variables under study in these two scenarios? And are they numerical or categorical? So in the parking garage example, what's the variable that we're looking at? Is it numerical? Is it categorical? Same thing for the carpal tunnel example. Again, think about these. We're going to be talking about them in class, but I want you to be thinking about how you would answer these questions. So go back and study those scenarios a little bit more. Try to think about what population is, what the sample is, and what are the variables under study. So if you go back and look at how we were asking those questions earlier, we used phrasing that was suggestive that we really aren't sure we're not actually shooting for a definitive answer. As I mentioned, since statistics can be thought of as the science of uncertainty. And so we're always answering things based on the sample that was drawn. And because we didn't gather information from the entire population, we're not going to know what the actual answer is about the population. But what we'll see is under certain circumstances, if we're careful, we should be able to expect that the answers that we get for the sample should very often not be too different from the answers that we would get for the population. And that's what one thing we want to try to understand in this course is that we can use sample information to say intelligent things about populations. I'll repeat that. A big part of this course is learning how to use sample data to say intelligent things about populations. So here's what we're going to be doing in the class. We're going to spend the first week or so dealing with chapters 1 and 2. We're going to go a little bit quickly at first, talk about kinds of data, the way we can collect data, and how we can summarize numerical and categorical variables. Chapters 3 and 4 introduce the notions of probability and random variables. Again, I'm not going to rush through it, but we're not going to take lots and lots of time on these chapters. So the first 4 chapters will go a little bit more quickly than maybe the later ones do. And it's because it's really in chapters 5, 6, and 7 that we really get to the heart of the course. We're going to be looking at ideas that were addressed in some of those example scenarios that we saw earlier, the notion of confidence interval and the notion of testing a pair of hypotheses. And so those are the things that we're going to take careful look at in chapter 5. And in chapter 6, then, we'll be applying those techniques to categorical data. And in Chapter 7, we'll be applying those techniques to numerical data. And we'll be spending a big chunk of our time in these 3 chapters in the course. And then at the very end, we'll introduce regression. And this is a way where we can study, look for, and say things about the linear relationships between a pair of numerical variables. So that's very briefly what our course is going to be doing. And so now let's just launch in and go to RStudio a little bit and look at a couple of data sets just to begin to get a feel for what it is that we're going to be doing here. And so the first data set that we're going to look at is NHANES18. And so there are 3 commands that load data into RStudio, allow us to see it, and bring up the help file that's associated with it. And those commands are data, view, and help. So please note, please note that view requires a capital V. RStudio is a case-sensitive tool, and so the D in data is lowercase, the H in help is lowercase, but the V in view is uppercase. And so these are commands, and so we'll often put arguments to these commands inside parentheses next to them. And in this case, NHANES18 is the name of the data set that we're interested in. So I'm going to copy and paste these in to the console in RStudio. So I'll paste these down here. I'll hit enter, and good things are going to happen. So we notice that we've got data in our environment window. We can actually see the data set up here in the upper left corner, and we've got our help file down here in the lower right corner. So just I'll be bouncing back and forth between RStudio and our slideshow for a while now. And so what we want to observe is that there are almost 10,000 rows in this data set, and we can refer to each of these rows as a case. And there are 18 columns, and so each column is going to represent a variable. We've got an ID associated with each individual, and then we've got data that's associated with each individual. We know their gender, their age, their education level, their marital status, information about cholesterol levels, iron levels, blood pressure, and then whether or not they have various maladies, various conditions here in the end. So we've got 18 different variables. And so we want to recognize that even though there are thousands of people included in this data set, it's still a sample. And let's think about just a second, what might the population be? Well, if NHANES is the National Health and Nutrition Examination Survey, national here is referring to a specific nation. It's the US, and so we were thinking that the population here might be US adults. So what are some examples of numerical and categorical variables in this data set? So if we go back and look at age, cholesterol, sodium, and systolic, these are 4 different numerical variables. Age, a number, cholesterol, a number, systolic, a number, sodium, weight, those are other numbers as well. So these are numerical variables. We can classify numerical variables as either discrete or continuous. Generally speaking, discrete variables are counting something. And so we might be counting number of years that we've been alive, or the number of beats per minute at a particular point when you're measuring blood pressure. So these are examples of discrete variables. We're counting something. Cholesterol and sodium the levels in the blood, however, are continuous. And since we're measuring things, and we can, if we wanted to, we can measure these values to any number of decimal places. Even though in this particular data set, it looks like the sodium levels have been rounded to the nearest integer. Strictly speaking, we're measuring something, and so we would expect those to possibly have decimal values, and so those are continuous variables. What about categorical variables? Well, here are 4 examples of categorical variables: gender, education level, income, and asthma. So let's take a quick look at that. Gender, we're classifying everybody here in this data set as either male or female. Education, there are 5 different possible levels. We'll go back to the slide just a minute and see what those are. Asthma just records whether the individual has asthma or not. And so, for example, education has 5 levels, as I said, under 9, which means they didn't get into high school, so they have a junior high, middle school education at best. Under 12, they made it to high school, but they didn't graduate. High indicates they graduated from high school. Associates means they attained associate's degree, 2 years of college. And bachelor means they have 4 or more years of college. Just a quick note what the NAs represent. We see several things here, several NAs, particularly in this income column. Just means that there was no data supplied. There was no response from that individual. And at the bottom of the slide, I show you that there's a difference between ordinal categorical variables and nominal categorical variables. An ordinal one is one for which there's some sort of natural ordering, like the education. Asthma would be an example of a nominal categorical variable. There's no ordering of variables. It's just yes or no, you have the condition. We're not saying that one of those is necessarily better than the other. I suppose people would rather not have asthma, but we would still say that that's a nominal random variable. So here's another question, a couple questions for you to consider as you prepare for our first class meeting. Can you come up with another ordinal categorical variable in this data set? And can you come up with at least 2 other nominal categorical variables in the data? So another thing that we're going to be interested in doing is thinking about when we have a data set, it's natural to ask, well, what are the questions I can ask about the data I've collected? And ordinarily, you would have the question framed before you began collecting the data, because you don't want to use the data that you collected to drive particular questions after the fact. But here are some types of questions that we might have come up with before we collected the information from in the NHANES 18 data set. Is there a difference? Do different genders have different systolic blood pressure levels on average? Do different education levels have some sort of different income levels? Does cholesterol change over age? So these are all types of questions that we might be interested in asking and using the data set that we have to explore. So, it's part of a natural scientific process. You have a question, you collect data to investigate the question, then you use the data to try to make an intelligent response to the question. So here's another data set that we're going to explore from time to time. It's MAT111 survey. This is data that was collected from a statistics class, much like yours, or a few statistics classes, sections of a statistics class several years ago. And so these were taken from Georgetown College students of a few years ago. And so again, I can copy and paste these values in to my console down here. And now I'm looking at MAT111 survey. And we've got various pieces of information. You can read over here in the help file what each of the variables stands for. That's a good place to go to understand what variables measure, what the different variables are measuring. And so we have here just 71 responses, 12 variables. And I'd like you to, again, look at these, look at the help file, look at the data, identify 3 numerical and 3 categorical variables in this data set. And again, we'll be talking about this when we get together. But I want to explore one particular possible investigation question here. Is there a relationship between a student's height and the fastest that they've ever driven? If we go to the data, we see that height is one of the variables, and fastest. And if we go down here to the help file, height measures how tall are you in inches, and fastest is what's the highest speed at which you've ever driven a car. And we might want to ask, is there some sort of relationship between these two variables? Notice that they're both numerical variables. We have numbers associated with each one of them. And so one tool that we have for exploring a pair of numerical variables is something called a scatter plot. And the command that we use in RStudio to do this is called xyplot. So xyplot, is the format for this is we call xyplot. And the simplest thing we can do is we can give the two variables, and we're going to put a little tilde in between the two variables. So fastest tilde height, comma, and then we need to tell RStudio where the data lives. And so data equals M111 survey. So let's copy and paste this and see what we get. And notice that we get something in the plot tab over here now. And so in our slideshow, we've got this as well. Here's our graphic, and we're wanting to try to see, can we say anything intelligent about the relationship between these two variables based on what we see. So first of all, I'll just notice that height wound up being the variable on the horizontal axis, and fastest wound up being the variable on the vertical axis. So if we go back to the previous slide, we have fastest tilde height. This apparently is the vertical variable, and this is apparently the horizontal variable. So vertical tilde horizontal. And so what do we see? Well, it's a bit of a blob, a cloud. But if we look at it a little bit longer, we can see that generally speaking, as height increases, fastest speed increases. So there's just a slight upward trend to the variable, to the plot as we read left to right. I know we've got these two values out here. We've got these two points up here, but generally speaking, there's a slight upward trend as we read left to right. And so we want to train ourselves to be able to see that. And so I would say we have a weak upward trend. And so because we see a pattern, we're claiming there's an association between the two variables. The two variables are associated. If there's an upward trend, as we see here, we're going to say that that's positive association. If we'd seen a downward trend instead, we would have said it's negative association. So I would want to say there's a weak positive association between height and the fastest speed ever driven. So let's step back here. We had two numerical variables. Even if we have, anytime we have two variables, they don't have to be numerical, but oftentimes we're going to be referencing one of them as the explanatory variable and the other one as the response. And so explanatory is the one that we expect to have an impact on the other one. The response one is the one that happens in response to the value of the explanatory. And we want to think about, well, between fastest speed and height, which one would you call the explanatory? It's not totally clear that one should be explanatory in this case, but I'm going to try to make a case for you that height should be the explanatory variable. And the reason for that is, height is, when you become an adult, as you are when you're college age, your height is something that's sort of intrinsic about you. And so in talking about which is explanatory, which is response, sometimes you want to ask which comes first. And your height, your final height, is something that's sort of intrinsic about you. It's probably what comes first. And then you get in a car after you've grown and you decide how fast you want to go. Another reason why we might kind of think that height should be explanatory is that different people have different heights, but we might suspect, and it seemed like it was borne out maybe slightly by the scatter plot that we saw, that males might want to tend to drive a little bit faster on average than females, and males are taller than females. And so we might think that there's some explanatory power there. And so But let's go back and think about the first one. Height is something that comes first. It's something intrinsic about you, whereas the fastest speed you've ever driven is probably not. And so let's go back to this command one more time. Which one got listed first? Well, the response variable got listed first. So keep that in mind. With a scatter plot, it's going to be response tilde explanatory. So explanatory is the horizontal variable. It's the one that's going to become second. The response variable is going to be listed first in XY plot. So we saw this weak positive association of the scatter plot. So what I want you to do now, try to do, is open the data file utilities, take a look at its help file. So notice that the U in utilities is capitalized. And then we want to draw a scatter plot for the two variables temp and CCF. And we want to be thinking about which one is explanatory and which one is response. So let's do that over here. Let's do data utilities. And then we'll do a view of utilities. And we'll do a help. So we want to look at temp and CCF. Temp is the average temperature, means average outdoor temperature in degrees Fahrenheit over a billing period. And CCF is the number of cubic feet of gas that have been used to heat or cool the home. And so temperature, average temperature, CCF, cubic feet used to heat or cool the home. Which one of those should be explanatory and which one is response? Well, which one happens in reaction to the other? Do we use gas in response to the outdoor temperature, or does the outdoor temperature happen in response to the amount of gas that we're using? Well, hopefully one of those rings a little truer than the other. So generally speaking, gas usage is going to happen in response to the outdoor temperature. When it gets colder outside, we're probably going to use more gas to run the furnace. And so it seems like temperature is going to be the explanatory and CCF is the response. And so the command for the scatter plot in this case then is going to be XY plot CCF tilde temp data equals utilities. So if I copy and paste that in over here, I get the scatter plot over here. I see it in my slideshow as well. And so what I see is that I get a reasonably strong negative association. As temperature goes up, I use less gas. And then it's mostly linear through this segment, but it seems to level off and curve off a little bit toward the end. So that's it for this slideshow. Hopefully you're thinking about the questions that I asked, and we will talk about those when we get together in class.